Okay, so today's going to be a relatively straightforward lecture. Like last class was the one where we did the big kind of climbing Mount Everest. And here are just a couple more sort of famous problems to get more practice. Let me review then at the uh, request of some students briefly what we did last time. So it's really a culmination of a bunch of discussion where we started discussing problems that are occasionally harder than they look, right? And at first glance, there's not much explanation for why they're harder than they look. But then we'll start doing these reductions. Oh, 3-sat, is that easier? No, actually, I can take any sat formula and turn it into 3-sat. This kind of thing. Same story for subset sum, max 2-sat, longest path, independent set, and so forth, right? And, the one feature they had in common is that these are all search problems. They're all problems where you're looking for something, right? It seems hard to find, but if you did find it, you would know it, right? If you're looking at an independent set of size k, it's easy to notice. So you can actually use just the fact that there exists a polynomial time verification algorithm. It's easy to verify a correct answer in this sort of meta proof, right? And so you need one idea is that, okay, I can think of a polynomial time algorithm as a polynomial size circuit where if I sort of think of copies of the memory over time, and in each location being like a node in a circuit. Okay, so most of these just get copied over, and then maybe 2 locations go in, write out one more thing. So there's some kind of massive circuit going from left to right. But if you start it with a polynomial time algorithm, then that's if you start it with a polynomial time algorithm, then in fact, the total size of the circuit will still be polynomial size. Okay. And so that was sort of step one of this meta argument. And then the next interesting part was trying to point out that, oh, that means that every search problem is a circuit sat problem, right? And this was best explained by Good Will Hunting. And but the high level idea is that, uh, when you're checking to see if your assignment is satisfying, right? And you spend some polynomial time thinking about it, right? There's some simple algorithm you can write. That itself is in principle a polynomial size circuit, right? There's some polynomial size circuit for verifying and checking the correct answer. So as a result, right? So every polynomial time algorithm corresponds to a polynomial size circuit. So let's say I'm doing independent set. Is there an independent set of size k? Well, you have an algorithm that can check if something's an independent set of size k. That implies there's a circuit that's of polynomial size that takes some vertex set in a graph and checks to see that it's a independent of size k in the graph. Okay, so there's some circuit that checks to see if the answer is even correct. That means if you can solve circuit sat, is there some way to make the circuit happy? Then you can solve independent set. Is there an independent set of size k? So that's the high level idea. Anything that can be verified in polynomial time can be solved by a circuit. So if you can figure out if circuits are satisfiable, you can solve anything where an algorithm can check that an answer is correct efficiently. So you put that all together, and what we've shown is actually, because the first question is, here's a problem. Is there an efficient algorithm? And by efficient, we're defining it as polynomial time, something better than brute force. And, it might not be surprising that something that looks as general as SAT or circuit SAT is hard. That seems challenging. But now we have sort of even a stronger formal argument. And in fact, all of these problems are equivalent as far as polynomial running times go. If you can do independent set in polynomial time, which might seem simpler, you know that you can solve SAT. We did that together in class. We know that means you can solve circuit SAT, which means you can solve Hamiltonian path or some other problem, that can be verified, right? So, okay. So, NP, which stands for non-deterministic polynomial time, that sounds like a lot, but that refers to any problem that can be verified in polynomial time, right? Which means that there's a brute force algorithm because you can guess everything. I mean, exponential time algorithm. Now, we know that circuit SAT and 3-SAT can solve any problem in NP because a problem in NP can be verified, so there's a circuit. Okay. NP hard means this problem can solve any problem in NP. So certainly circuit SAT and 3-SAT are NP hard, so it's at least as hard as any problem in NP. That's what NP hard means. Okay. But also independent set is NP hard because independent set can solve 3-SAT. Hamiltonian path is NP hard because Hamiltonian path can solve 3-SAT. Okay. And then if you take what are the problems that are in NP and NP hard, okay, there's some Venn diagram. They overlap. That overlap is called NP completeness and it has the property that if there's a polynomial time algorithm for one, there's a polynomial time algorithm for all. And it's still an open question. We kind of feel like you probably can't solve SAT, but we cannot formalize this. And people are trying very hard. In fact, I don't even know if they're trying as hard anymore because it's so disheartening. People have over time put a lot of effort into this. This would be, the outstanding question, of mathematical science. Okay, certainly of computation. Okay, so that's the idea, and that's the terminology: NP, NP hard, NP complete. Okay, so it's an interesting landscape, right? When I first started taking algorithms classes, we're doing dynamic programming, we're doing, the shortest path, we're having fun. I never expected, something like this to emerge, right? Which seems more kind of philosophically interesting. Okay, so I've teed up two more problems. I won't survey. These are just going to be NP hard, and then the fun part is going to be trying to come up with reductions. Okay, by now I think I won't fool you anymore in these surveys. And they're also, this isn't graph coloring independent set. This is supposed to be graph coloring and dominating set. Off to a good start. Okay, we'll see. I think we can do both. Okay, so graph coloring. So I give you an undirected graph, and the goal is to color the vertices. So I can put like red here, blue here, green here, so that if I look at any edge, the two endpoints have different colors. So I want to color vertices so the endpoints of an edge have different colors, and I want to use as few colors as possible. Okay, so I'll let you guys look at this and tell me how few colors you can color this in. This might be a little bit hard to do in your head, but four, five. All right, who was able to get five? I know it's really hard to like stare at this and remember the color. And then anyone else try to get four? Okay, whatever. So what I'll do is I'll point to a vertex. You could tell me which color you want me to color it in, and you can really choose any color because we have an iPad. So okay. All right. So this top left vertex, what color should I give it? Pink. Okay. What's a good, like this kind of pink? Hot pink? Okay. How about this vertex? It's got to be a different color. Okay, we got that. Good. All right, how about up here? Black. Okay. Things have taken a turn. Okay. All right. How about this one? Remember, the goal is to use as few colors as possible. So don't everyone just shout out a different color with every vertex. Yeah. Because someone wanted black. I don't know. Okay, you want pink? I'll give you pink. Okay. All right, but now we're back to this vertex. Fuck. Okay. All right, I'll go to the left now. How about this one? All right, lavender again. All right, how about this one? Black. Okay, how about this one? Got it. Is that orange enough? Sort of a darkish orange. Okay. How about this one? Pink. Maybe on the bottom left? Pink. And then finally, okay, so we were able to do 4 colors. Is there any way to get 3? Are you sure? Ah, okay. So if you have, this is called a clique when you have vertices that are all connected. But up here you have 4 vertices that are all connected to each other. So you can't do better than 4 because those already require 4 colors. Good, good. Sometimes it's not so obvious that you can't do better, but here we can actually show it. Okay, so you get the idea. Um, so of course I can turn this into a yes/no question by saying, oh, is 5 colors enough? And you just have to answer yes or no. Um, And then sometimes you can pose as like minimum number of colors, or you can say K coloring, where like K is like part of the name of the problem, so you can treat it as a constant. So like 3 coloring, 4 coloring, 2 coloring, just like 3 sat, 4 sat, 5 sat, right? So when K is part of the name like this, and K is a fixed constant, like an n to the K running time counts as a polynomial. If K is part of the input, that's not a polynomial because you only need, log n bits to express K. Or yeah. Okay. Um, okay, so again, no surprises today. Well, maybe this part is surprising, is that we're going to be able to show that 3 coloring, which is a pretty small choice of K, is NP hard. Maybe as a fun trivia question, can I go lower? Can I show that 2 coloring is NP hard? Yeah? Yeah, so if a graph is 2 colorable, say in lavender and hot pink, then it has to have, some form like this, where I roughly have 2 vertices on 2 sides, and every edge is going from purple to pink, right? So you can basically do anything you want. You can just start coloring things like willy-nilly. Oh, I'll start here. I'll color this one purple. I'll color all its neighbors pink, and I'll just recurse. So you can just strap it onto your BFS or DFS thing. And if you run into some problems, it can't be colored. Otherwise, you'll just terminate successfully. Okay, so 2 coloring is actually rather easy. And 3 coloring turns out to be where it's hard. So there's something magical about the number 3, right? 2 sat was easy. 3 sat is hard. Max 2 sat was hard. So, okay. All right, so here's our higher level approach. We're going to start with 3 sat. That seems like a good candidate because it's 3 coloring. And we're going to eventually try to show 3 coloring is hard. But we're going to go through an intermediate problem, which is a little bit more convenient So I'm going to introduce something called subset 3 coloring. So subset coloring is also a problem. Oh, maybe I should mention for context. Um, why do people want to color graphs? Uh, okay, so I'll give two reasons. One is it's like an old math combinatorial topic. Like people, there's like very, very fancy theorems for absolute bounds, like related to the maximum degree in the graph, like Ising's theorem. The other though, like a basic application could be like you have a bunch of like cell phone towers, okay? And you want to assign frequencies to them, but you don't want the neighboring radio or cell phone towers to clash. So you want to assign different frequencies or bands or whatever. I'm just making up words, but you think of those as different colors, okay? And then you don't want the neighboring towers to have the same color or same frequency band. So that comes up uh, a lot. So it's really like conflict-free choices, right? You're assigning one of a bunch of different choices to each vertex, and then the edges say neighboring things can't choose the same thing. Okay, but anyway, on to the subset 3 coloring. Okay, so it's a little bit more general. So in 3 coloring, I can use any one of the 3 colors for every vertex. And here, for every vertex, I'm going to give you a subset of the colors. Okay. So I might say, oh, this vertex can only be colored color 1 or color 2. That might be hot pink and lavender. Okay. And then maybe the unmarked ones can have any color. So this one can only be 2 or 3. This one can only be 1 or 3, 2 or 3. Okay. So this is a more general problem, right? And it's going to be useful for us because I want to take 3SAT and turn it into a coloring problem. So to have a few extra degrees of free, a little more versatility here might make that transition easier. And then I can figure out how to take this general problem and try to solve that with 3 coloring in a separate stage. Okay, as opposed to trying to do everything at once. Okay, so that's the idea. So we'll start with the second leg first. So I start with, again, it's clear that this is more general than this. So if you just had 3 coloring, you could easily solve subset 3 coloring. But the real question is, if you had subset 3 coloring, could you still solve 3 coloring? This is sometimes also called list coloring. Anyway. Okay. So that's what we're going to try to do. We're going to try to take as input a subset or list coloring problem and turn it into a 3 coloring problem, and hopefully yes and no's will correspond. Okay. Do I have any ideas? I do. Good. All right, so here's your input. It's some kind of subset 3 coloring problem. Any ideas for how to turn this into a 3 coloring problem? Yeah, yeah. Okay, so you want to try to create a gadget to, okay. So what might the gadget look like? So if I had a gadget that could somehow say like this vertex is not allowed to use color 1 or something, that would be great, right? So for example, suppose, if I just like randomly could create, like if I could create 3 vertices, which I'll call 1, 2, and 3, that are where 1 is guaranteed to be colored color 1, 2 is guaranteed to be colored color 3. We'll have to figure out how to force this in a moment. And 2's color 2 and 3 is color 3. And then if I add an edge like this, it's saying, okay, this vertex cannot be colored 1, right? And this is saying, okay, this cannot be colored 3 or something. And I can add those lines, and then I don't have to explicitly write down these sets anymore. It's encoded with these lines. Okay, good. But now we just have to create something like this, because this is still cheating, because we force some colors. Yeah. Okay, so right now, first I made dummy nodes for the three colors, but now you want me to make a dummy node for not color one, not color two. For every node in the original graph, I'll make another dummy node. Okay, so I already have one. Okay, so here's a dumb node. So what should I do with this dumb? Yeah. Okay. So I can color this one, two, three. Sorry. If I connect them all with edges like this, then at least they have to have different colors. Huh? A good question. Good question. But at the very least, these three nodes have to have different colors. And at least in my mind, I can say, okay, I'm going to interpret this one as the one that has to have color one. This one has to have color two, and then add the edges accordingly. Okay, so let's do that and then come to your question. So I've drawn this. Uh, yeah, so I think of it as like a color palette. Um, and so you have something like this. Um, okay, so this is now the question is, uh, how am I really forcing like this one to be color one and that one to be color two and that one to be color three? Yeah. Um, okay, so all right, so the claim was that it doesn't matter. So right. Um, yeah. Sorry, what was your question? Yeah, yeah. So if I don't know, if this vertex only had one, it would have two edges coming down from the palette saying, "Oh, you can't use two or three." Okay. Okay, so maybe we can go through it slowly, right? So we just have to show you can go back and forth. So if you had a solution that was a subset coloring, so it really gave this color three or color one or two, and it gave this color two or three, and so forth, right? Then I can extend that to a coloring up here by just coloring one, two, three like I wanted. And that'll give me a proper three coloring of the graph, right? Because, all of this is colored okay. And the way this is set up is that, oh, this one is going to get color one. It's only attached to things that are getting color two or three. So if you had a subset coloring, it's not hard to color everything just by adding colors up here. Okay. Now, vice versa, suppose you give this to your three coloring and it produces a three coloring of this graph. Okay. So what we're going to do is we're just going to give it like, we're going to choose different names for the colors. So let's say that we're thinking we start with numbers one, two, three, but the box is just going to give it three. And I tell the box, oh, color it lavender, pink, or yellow. Okay. So it's going to do some kind of lavender, pink, or coloring. So maybe this is purple and this is pink and this is I'll give it a different color, maybe navy or something, right? And it's also going to give the top colors some kind of colors, right? So let me just make sure I do this correctly. So maybe purple here. Uh, okay, so Yeah, so it's true. The black box has no idea what the original numbers are because what I feed to the black box is going to hide these sets. It's only going to look at these vertices and edges. And I'm going to say, okay, color it navy, lavender, or pink. They actually look kind of similar, huh? But that's okay. Um, okay. And now I'm going to look at this and I'm going to say, okay, I know what I kind of wanted. And I'm going to say, oh, I wanted this vertex to be color 1 in the original problem, right? So I'm going to say, okay, pink is color 1. Color 1 for the original problem. So the original problem was 1, 2, or 3. I give it to the black box. It gave me pink, purple, or navy. And I get to choose how to interpret pink, purple, and navy. Pink, lavender, and navy. I apologize. Right? So I'm going to say, oh, well, this is the auxiliary vertex that I had, color 1 in mind for. So I'm going to call everything that was pink down here is going to be color 1. And everything that was lavender is going to be color 3. And everything navy is going to be color 2. And now we just have to check we satisfy all the subsets, right? So take this one here. This one can be color 1 or 2. It can't be color 3, and there's going to be an edge attached to lavender, which is what I think of as color 3 now. So it's not going to get assigned color 3. So yeah, it's true that so you can just read off from here what color 1, 2, and 3 are supposed to be in an original problem. And then you just go through, you carefully check. And that was our 2 directions. Okay, so it's a cute trick. Yeah, I think of it as like those color palettes that like an artist holds in their hand, if such people exist anymore. Okay, so that's step 1 for us. That kind of construction. So now we have to bring 3SAT into the fold. We have a little bit more flexibility now because as opposed to going straight to 3 coloring, now we have these subsets at our disposal. We'll see why it's convenient in a moment. So we're going to take a 3SAT formula and try to turn it into a subset 3 coloring problem. Okay. All right, so good. So any ideas? High level ideas. How to start with a SAT formula, try to make our way over to a coloring problem or generalized coloring problem. Oh, okay. Um, so I have a node representing x1, x2, say x1 or x2 or x3. And then I have 3 colors, which I guess is something like x1 equals true, x2, x3. And I would do that for other ones, x4, x5, or x6. Something like this. Or maybe if it's not x5, it would be not x5 as a choice. Okay. That's quite reasonable. At least it makes sense with 3. Although one thing I'll point out is that, yeah. Okay, we'll do that idea next. Okay, so the other idea was what if the colors correspond to true or false? So you have to probably figure out what the third color is, but yeah. But one thing I want to point out here, though, is that in our subset 3 coloring problem, all the subsets were out of the 3 possible choices. Whereas here, you have 1, 2, 3, 4, 5, 6, plus their negation, 7, 8, 9, 10, 11, 12. So you're going to have many total choices out there. So the pattern matching to 3 actually doesn't quite work out. Okay, so another idea is somehow the colors, we'll start with the colors. Maybe the colors is equal to true, false, and then I'll name the third color nonsense or something. Okay, just to give a third color. So, okay, so if our colors are going to be roughly assignment values plus some third ambiguous color, what might a vertex look like? Well, what would be the vertices? Yeah, yeah, every literal, um, okay, so each of these could be, either true or false or something, right? And since I am not allowed to, um, since I'm not allowed to assign true to both xi and xi bar, uh, I can add an edge in between. Okay, so this seems like a reasonable start. Assigning colors to vertices at least corresponds to assigning true or false to our variables, and or at least we're getting the whole like, okay, you can't set it to true and false. Yeah. So what have we not done yet? Yeah, we haven't modeled the clauses. Yeah, so we sort of have one bullet in the chamber. Maybe we'll make use of that third color. Um, uh, but we haven't figured out how to model. This is the right start actually, but we have to somehow figure out how to model clauses. Okay, we're gonna do three step, but maybe as a warm up. Suppose I wanted to model uh, just a two variable formula, something like this, right? So somehow I want to make some gadget where x1 and x2, I mean, that somehow you can only do a coloring or something if the clause is satisfied, right? So your gadget will probably involve an x1, your vertex for x1 and your vertex for x2 bar, and these can be either true or false. It would be nice to kind of extend it to some kind of small graph or gadget or something where I can only color the whole thing properly if I either set x1 to be true or x2 bar to be true. Yeah. Um, yeah, so for this clause, yeah, if they're both true, it'll return true, and if one of them are true, it'll return true. Hmm. Well, this is two different vertices. So you have two vertices, two different colors, so that's okay. Um, so I think as a thought experiment or like as a warm up, our goal is to eventually turn an entire three-sat formula into a graph coloring problem. We have this extra flexibility of subsets. We've already come to a point where we feel like, okay, I should have a vertex for each literal that can be true or false. That makes some sense. But I need to somehow add some vertex graph to model like the fact that this needs to be satisfied somehow, right? So yeah, so Yeah, you had a suggestion. Okay, so here's the first one that you might think of that wouldn't necessarily work. If I added just an edge between these two, then you're not allowed to set, so you shouldn't be allowed to set both of them false, right? That's what we really want to show. You can't set both of them false. And if you put this edge, okay, you can't set both of them false, but the problem is you also can't set both of them true, and you might want to set both of them true. So adding an edge directly in the middle might not help, okay? Um, Now we can add something like this, and so I can add a vertex like this, and I should only be able to color the vertex if at least one of them is not false, or something like this. Yeah. Oh, I guess I mean the variable corresponding, or the literal corresponding to the vertex I'm assigning to true or false. So probably just like if I had given the color true or false. I'm being a little bit informal or imprecise with my words. Basically, I get excited and all the words mash together. Um, so is there a subset that I can assign to this vertex? So this vertex is colorable only if I don't choose false false. Okay, if I did nonsense and false, okay. Now the catch though is if I did false false, I can still color it nonsense. And if I only did false up there, then true false I wouldn't be able to color either. So okay, that doesn't quite work either. But if you keep going, okay, um, okay. So how about this kind of construction? Okay, this is just like if we just kept adding edges and kept playing around with small graphs. Okay, so here's the original variables like x1 and x2 from before. Now it's called a and b. And so this can be true or false or true or false. These two intermediate vertices can be anything. And the top one can be either true or false. Okay. And so my claim is that you can only color this thing to be true uh, if A or B is equal to false. I hope that claim's correct. We'll find out. Okay. Does that make sense? So C is a brand new thing. The top part, I mean, this is all the new stuff, and only the two vertices is what we started with. So that's going to be our OR gadget. Okay. Um, so, okay, so how can we do this? So if we assign this to be true, right? Then if I actually made C true, then one of these has to be false and one of these has to be nonsense. Okay. But the one that's false forces A to be true. I think so. Okay, and then okay, conversely, if you had, say, true or false, Um, oh, did I mess this up? Oh, sorry. You can make this true. Um, because, right, you can make this false, you can make this nonsense, and then you can make this true. Okay, good. So that's okay. Same with true, true, false, nonsense, true. And then false, true is the same as true, false. Okay, good. So that will let you do two variable clauses. How would you do three variable clauses? Oh, it's on the right. Yeah. Okay, so you can compose these things, right? So kind of something like this. And and then this one has to be true. The overall clause has to be true. And that's only possible if this is the same clause, this or this is true. So either this is true and you're just happy, or this is true, in which case either this or this has to be true. Okay, and up here I said you can only choose true because you have to make this clause happy. Okay, so that's how you do it. Okay. Um, oh, that's yeah. It could, but if this is true, then at least one of these has to be false. This could be false and this could be nonsense, or this could be nonsense, this could be false, because they're connected in a triangle. In which case, if this is false, then this has to be true. If it's nonsense, this could be anything. And if this is false, this has to be true. Oh, the typo was reintroduced. Um, but ultimately, you just need to check both directions of this if and only if, and then it'll work the way you want. Yeah. So this complicated thing is just two of these combined. Okay, so that is how you go from 3-sat to subset 3 coloring. And we didn't do this, but it's okay. So maybe I'll just explain what the problem is and that it's also NP hard. And actually you might even be able to think of how to do this one on your own, but at the very least it's described in the notes. So this is a problem where I also give you a graph. And a dominating set is a set of vertices. It should look like, it's probably, you want to make it small, and you want to guarantee that every vertex in the graph is either in your set or it's a neighbor to some vertex in your set. Okay, so everyone should be like in your set or one hop away. That's a dominating set. And the problem is to come up with a minimum cardinality dominating set. Okay, so I'll end it there. This one also turns out to be NP hard, but the construction is a bit less elaborate than the graph coloring one we just did. Okay, thank you.